Dark matter still looks like a substance. Physicists refer to it as invisible mass scattered throughout galaxies, pulling stars into their orbits without emitting light. But that clean explanation is already showing cracks. The Large Hadron Collider has smashed particles for over a decade without creating a single confirmed dark matter candidate. Giant, hypersensitive detectors buried a mile underground have sat silent for decades, waiting for a hit that never happens. And on the cosmological scale, bizarre galaxies appear to have no dark matter at all, which is difficult to explain if it is supposed to be a fundamental substance. What looks like a missing mass problem is really a missing physics problem, and the consequences spread from there. That one visible failure already tells you the system is more complicated underneath. Through a forensic lens, dark matter is not a solved category. It is a label that may have biased the entire community to search for a substance, rather than question whether the law of gravity itself is incomplete. By the end of this case file, you will understand exactly what that clue means, and why 50 years of silence is not a delay, but a diagnostic signal that the framework may have been wrong from the beginning. That is not a projection. That is the system behaving exactly as the evidence suggests. We view dark matter as the invisible scaffolding that holds galaxies together, but through a forensic lens, dark matter is not scaffolding. It is a placeholder for something we do not yet understand about gravity at cosmic scales. And the longer the particle hunt continues without results, the more that placeholder looks like a conceptual mistake rather than an undiscovered substance. The first visible clue comes from the collider side. The Large Hadron Collider was designed to probe the fundamental structure of matter by accelerating particles to near light speed and recording the debris from their collisions. High-luminosity upgrades are expanding the hunt for rare particles, pushing the machine to deliver more collisions and more data than ever before. But the deeper tension is that increasingly powerful machines and increasingly sensitive underground experiments still have not delivered the kind of clean, missing particle confirmation many expected. The leading particle candidate, the weakly interacting massive particle, has been almost entirely ruled out by experiments, leaving the theory in a corner. For half a century, physicists have directly searched for dark matter particles and found absolutely nothing. That result is not as simple as it looks. If dark matter were a substance, the detectors should have registered something by now. The silence is not neutral. It is diagnostic. It tells you that either the particle is far more elusive than any model predicted, or the search itself is aimed at the wrong target. Now look at the galaxies themselves. Astronomers measure how fast stars orbit around galactic centers, and compare that speed to the visible mass inside the galaxy. According to Isaac Newton and Albert Einstein, the visible mass is not enough to generate the gravitational pull required to keep those stars in their orbits. They should fly apart. Instead, they hold together as if something invisible is adding extra gravity. That invisible something was named dark matter. But the name itself encodes an assumption. It assumes the missing force comes from missing mass. It does not ask whether the force calculation might be wrong. Modified Newtonian dynamics, a theory proposed in the 1980s, perfectly predicts how galaxies rotate using a simple tweak to gravity without needing any invisible matter. The theory says that at extremely low accelerations, the kind found at the edges of galaxies, gravity pulls harder than Isaac Newton's equations predict. That single adjustment matches observations across hundreds of galaxies. Visible mass scales perfectly with rotation speed, a relationship called the baryonic Tully-Fisher relation. The precision of that scaling suggests a law of physics rather than a random cloud of particles. If dark matter were a substance distributed differently in every galaxy, you would expect the relationship between mass and rotation to vary. It does not. The pattern is too clean. That is the first structural crack. The system also shows that labeling the mystery dark matter biases the community to look for a substance rather than questioning if the law of gravity is broken. The name creates a search strategy. If you call it matter, you build detectors to catch particles. If you call it a gravity problem, you build tests to measure how gravity behaves at cosmic scales. For decades, the particle search dominated. Funding, careers, and experimental infrastructure were built around the assumption that dark matter is a particle waiting to be found. That assumption is not neutral. It shapes what questions get asked, what experiments get funded, and what results get interpreted as success or failure. The cosmological constant problem adds another layer. Vacuum energy, the energy of empty space predicted by quantum mechanics, is off by 120 orders of magnitude when compared to observations. That is not a small error. It is the largest discrepancy in the history of physics. It suggests our basic equations for the large-scale universe are fundamentally wrong. Some physicists argue that if the equations break down for vacuum energy, they might also break down for gravity at galactic scales. The two problems could share a root cause. String theory, still unfinished after decades of work, proposes that gravity might be leaking into higher dimensions, making it appear stronger or weaker than our three-dimensional models predict. That leakage could explain why galaxies behave as if they have more mass than we can see. But string theory has not yet produced a testable prediction that distinguishes it from other explanations. The theory remains conceptually promising but empirically silent. And that silence mirrors the silence from the particle detectors. Both searches are looking for something that has not yet appeared. To understand the horror of the dark matter model, we have to look at what happens when the substance assumption meets the data. Astronomers have found galaxies that appear to have no dark matter. These galaxies rotate at speeds that match their visible mass exactly, with no need for an invisible component. If dark matter is a fundamental substance that forms the backbone of galaxy formation, these galaxies should not exist. Their presence suggests that whatever is causing the extra gravity in most galaxies is not a universal substance, but a conditional effect. That effect could be gravitational. Modified gravity theories propose that gravity has two speeds. At high accelerations, like those near the surface of Earth or inside the solar system, gravity behaves exactly as Isaac Newton and Albert Einstein described. At extremely low accelerations, like those at the edges of galaxies, gravity becomes stronger than expected. The transition happens at a specific threshold, and that threshold appears in galaxy after galaxy with remarkable consistency. The same tiny acceleration constant appears in both galaxy dynamics and cosmic expansion, hinting they are the same gravitational mystery. If the threshold is real, it is a law of nature, not a substance. One radical idea proposes that space-time itself turns into a superfluid at cosmic scales, creating extra drag that we mistake for matter. Another theory, called entropic gravity, suggests gravity is not a fundamental force, but an emergent property of information, like heat arising from moving molecules. These theories are speculative, but they share a common insight. They treat the missing gravity problem as a signal that general relativity is incomplete, not that a new particle is hiding. The system creates a reinforcing failure loop. Every year that passes without a particle detection strengthens the case that the search is aimed at the wrong target. But the infrastructure built around the particle search is enormous. Detectors cost hundreds of millions of dollars. Careers depend on the assumption that dark matter is a substance. Shifting the framework from missing matter to missing physics requires not just new data, but a willingness to abandon decades of investment. That resistance is not irrational. It is structural. Science does not turn easily when the system is designed to move in one direction. The deeper problem is that the standard dark matter theory predicts thousands of satellite galaxies around the Milky Way, but astronomers have only found a few dozen. That discrepancy, called the dwarf galaxy shortage, has been known for years. Modified gravity theories do not have this problem. They predict fewer satellites because they do not rely on vast halos of invisible matter to seed galaxy formation. The mismatch is not fatal to the dark matter model, but it is another crack in the surface. And the cracks are accumulating. Now look at what happens when you test the two frameworks against a unique prediction. Modified gravity predicts an external field effect, where a galaxy's internal spin is affected by a neighbor's gravity. Dark matter particles cannot do this because they respond only to the mass inside the galaxy, not to distant gravitational fields. Observations have detected the external field effect in multiple systems. That detection does not prove modified gravity is correct, but it does show that the effect exists. And the dark matter model has no natural explanation for it. The tension is not just between two theories. It is between two ways of understanding what the universe is made of. If dark matter is real, the universe contains a vast, invisible ocean of particles that outweighs all the stars, planets, and gas combined. If modified gravity is correct, the universe is made of the same matter we already know, but the rules that govern how that matter interacts over vast distances are different from what we thought. One view adds a new substance. The other view changes the law. History shows science often invents substances to explain phenomena that actually require entirely new laws of nature. Before James Clerk Maxwell unified electricity and magnetism, physicists believed space was filled with a substance called ether that carried light waves. Experiments eventually showed the ether did not exist. The wave behavior of light required new physics, not a new substance. Critics compared dark matter to Ptolemy's epicycles, complex mathematical fixes used to save a dying theory instead of accepting a new reality. That comparison is not proof, but it is a warning. When a theory requires more and more adjustments to fit observations, it may be time to question the foundation rather than add another layer. The system also shows that background neutrinos are about to drown out dark matter detectors, making it physically impossible to find particles using current methods. This threshold is called the neutrino floor. Once detectors reach that sensitivity, any signal could be a neutrino rather than a dark matter particle, and there is no way to tell the difference. Some experiments are already approaching the floor. If dark matter particles exist, but interact even more weakly than the current detection limit, they may be permanently out of reach. That does not mean they are not there. It means the search strategy has hit a physical wall. But the silence from the detectors is not the only clue. Gravitational wave observations are finally catching up to century-old predictions. When two black holes merge, They send ripples through space-time that travel at the speed of light. Those ripples were detected for the first time in 2015, confirming a key prediction of general relativity. In 2017, astronomers detected gravitational waves from two colliding neutron stars and measured the speed of those waves with extraordinary precision. The waves traveled at exactly the speed of light. That measurement ruled out many modified gravity theories that predicted gravitational waves would travel slower or faster. But it left the most radical ones standing, including theories that modify gravity only at low accelerations or propose that gravity leaks into extra dimensions. The observation did not settle the debate. It narrowed the field. You, the viewer, should watch how the language around dark matter shifts over the next decade. If the particle search continues to come up empty, more physicists will begin to use the term dark gravity instead of dark matter. That shift is not just semantic. It signals a change in the underlying framework. Calling it dark gravity moves the focus from finding a new particle to fixing a broken law of physics. It reframes 50 years of null results not as a failure to detect something, but as evidence that the search was aimed at the wrong target from the beginning. Shifting the label from dark matter to dark gravity is not about giving up. It is about reading the system more carefully. The visible clue is the silence. The hidden mechanism is the possibility that gravity itself behaves differently at cosmic scales than it does in the solar system. And the consequence is that the universe may not need a new substance to explain what we see. It may need a new law. So, here is the answer to the question from the beginning. This is what that clue means. 50 years of silence from particle detectors and the discovery of galaxies with no dark matter suggest that the missing mass problem is really a missing physics problem. And the name dark matter may have biased the search toward a substance rather than a broken law of gravity. That is not a projection. That is the system behaving exactly as the evidence suggests. Dark matter is not solved yet, but that is the point. The conflict is in a framework that still looks solid from the surface and no longer fits cleanly with the data underneath. Most people see the missing mass. Now you can see the missing physics.